So what are we doing? How do we solve this problem? Well, first, I like to start with a picture. So we got a box for a valley that has a volume. And let's give it some dimensions. So 200 meters deep, 2 kilometers wide, and 5 kilometers long. $200 should probably be this, but that's not important for what to do to solve this problem. So we got our box. What's the volume of this? Well, that is equal to length times width times height. And we're not all in the same units, so this is equal to 0.2 kilometers. Because there's 1,000 meters per kilometer, or 1 kilometer per 1,000 meters. So 5 times 2 is 10. 10 times 0.2 is 2 kilometers cubed. Alright. And what are we searching for again? So ppmv of I-131 equals what? Well, we know that the mass of iodine is equal to 120 kilograms. And we know that the definition of ppmv is milligrams per liter divided by molecular weight times parts per million volume times the volume at given conditions. The molar volume. Ideal. And since we're at 20 degrees C and we're at 1 atmosphere, we can assume ideal conditions and use the ideal gas law, which is PV equals nRT, to find the molar volume to use for determining ppmv of iodine 131. So when you plug in, T is equal to 373 Kelvin, because Kelvin is Celsius plus 273.15, and it's at 100. Oh wait, no, it's not 373. So D is equal to 20 degrees Celsius, which equals 293 Kelvin. R is equal to 0.08206 liters atmosphere per mole Kelvin. Units. That's how you know what R to use. V is equal to, that's what we're finding. P is equal to 1 atmosphere, and we can assume N to be equal to 1 mole. So V ends up being 24.505 liters. So now we can determine the parts per molar volume. Parts per million volumetric mole, ppmv, using this volume as for the volume that we use to calculate the concentration of iodine of this 120 kilograms of iodine evenly mixed within our valley. And we know that 1 cubic meter has 1,000 liters. And there's 10 times, or 1 times 10 to the 6th well, 1 kilometer cubed has 1 times 10 to the 6th meter cubed. And in 1 cubic meter, there's 1,000 liters. So the concentration of I-131 is equal to 120 kilograms per two times 10 to the 9th liters. And this is also equal to, well, we can convert kilograms to milligrams for our parts per million. So in 1 kilogram, there are 1,000 grams. And in 1 gram, there's 1,000 milligrams. So the units cancel. You're left with 1.2 times 10 to the 678 to the 8th milligrams per 2 times 10 to the 9th liters times 24.505 liters divided by the molecular weight, which is 131 grams per mole. We know that from 131, and this needs to be converted to milligrams. So there's 1,000 milligrams in 1 gram. Liters cancels with liters. Grams, grams. This milligrams will cancel with that milligrams, and we're left with moles. Parts per million molar volume. So the ppmv is equal to 1.101 times 10 to the 5th. Voila. So what did we do in order to solve this problem? So first we drew a picture so that we could find our concentration of iodine. We knew 120 kilograms was released and perfectly mixed within a 2 kilometer cubed volume, metric space, a cube, based off the problem statement. The temperature and the pressure were given, so we could solve for the ideal molar volume conditions. With that, using the definition of parts per million volumetric parts per million, we were able to solve using some unit conversions to get the ppmv of this situation for 121.